And our final talk is by Stefan Appelhoff from the Max Planck Institute for Human Development. And his talk is titled Control Over Sampling Boosts Numerical Evidence Processing in Decisions from Experience.
Yes, hi everybody. Can you see my slides?
Yes, we can see the slides.
Okay, cool. Today I want to present some results from my current study that shows that control over sampling boosts numerical evidence processing and decisions from experience. And the big research question for this study is how does control over sampling impact choice? And it's motivated by the fact that for many decisions, humans can base their choice on sampling experience. However, this sampling can differ quite strongly in terms of the actual control over the process. For example, when buying a car, you can decide both which cars to try and for how long to try them before buying them. However, when you do a standardized job interviews, you may only get 2 applications and you have to select a single one of them. Previous research has shown that this control over sampling does impact the final choice. And in our study, we are interested in how the neurocognitive mechanisms are affected by that, or how they affect that. Specifically, we are using a numeric sampling paradigm where participants first sample numeric outcomes between 2 options. And then after some time, they make a one-shot final decision for one of those options and get a reward for that. And the reward comes up in the form of a random draw from that finally chosen option. And crucially now, we vary the amount of control that participants have over the sampling process. In full control, they decide both where to sample and for how much to sample. Whereas in partial control, they only decide where to sample. And after a fixed number of 12 samples, they have to make that choice. So here the number of samples is fixed. And finally, both of these these conditions have control conditions or baseline conditions that are associated with them, where participants only see a replay of the sampling and they have to base their final choice on that replay. Now let's turn to the results. To check whether the control over sampling truly influenced the final choices at all, we had first a look at the behavioral accuracy. And here we saw that participants were significantly more accurate in identifying the option that was more profitable when they had full control over the sampling as opposed to only partial control or no control. We then also wanted to see whether the integration of sampling information over time was different. So we calculated decision weights for early, mid, and late samples in the sampling sequence. And we found a clear recency pattern overall in that late samples had a higher weight than earlier samples in the sequence. However, this did not show to be any different between the different sampling conditions. The recency was approximately the same. So much for the behavioral data. Next, we looked at our EEG data to get an insight into whether early visual perceptual processes differed between the conditions. For that, we looked at 2 early visually evoked potentials, the P1 and the N1, and compared the amplitudes. However, it turned out that the amplitudes were absolutely comparable, and so there was no difference between full, partial control or no control in terms of these early visual processes. Okay, now we know that early perceptual processes are not strongly affected by the level of control over sampling. But what about later cognitive processes? And to shed light on that, we made use of earlier findings by Spitzer and colleagues 2017, who showed that in a different numeric paradigm, participants encoded the number information along a neural number line so that the multivariate representation of a 1, for example, is closer to the multivariate representation of a 2 than it is to a 5, for example. And in our study, we harnessed this finding to see whether the number line encoding is different between levels of sampling control. And our results show exactly that, as you can see in the plot. Firstly, there's a number line encoding in all of the sampling conditions. But secondly, this effect is significantly stronger under full control, but not partial or no control over sampling. And in split analysis, we furthermore showed that this effect is present throughout the whole sampling sequence. That is, it arises early on. The final result I want to show to you today is based on the question whether the accumulation of sample evidence differed between conditions. And for that, we looked at the amplitudes of the P3 ERP component in early, mid, and late samples over the sampling sequence. And interestingly, the accumulation was steepest under full control again, as can be seen in the plot on the lower left. And now showing this as a summary plot together with the no control baseline conditions, we see that the accumulation happened in every condition, but significantly steeper in full control. And this is again mirroring the same findings that we found for behavioral accuracy and for the number line encoding. And that already brings me to my summary, that control over sampling boosts numerical evidence processing. And we found that under full control over sampling, there was a higher accuracy. There was no difference in early visual perceptual processing. However, we did find a stronger encoding of numerical information that was evident early on in the sequence. And finally, steeper accumulation of evidence in neural signals. However, no difference in evidence integration in the behavioral data. I want to thank my collaborators and supervisor Bernhard Spitzer and Ralf Hertwig, my lab and data collection team, and of course you for listening and joining.
Great, thank you, Stefan. That was I mean, it's super interesting. I like the idea of the number line, like the numbers encoding strength being particularly important for the decision making here. I'm wondering I like that idea. I'd like you to explain it a bit, like just a bit more for me, like why the strength of the similarity to the neural number line should be the determinant. Do you think that this is driving people more toward like making the decision drive closer to this decision boundary because their kind of internal representation of the number is stronger, or is it some other type of process?
So I think it could go into several ways here. So if participants have a stronger encoding of the numbers in the space, in this paradigm, the numbers also directly relate to a reward. So a 9 also means a higher reward than an 8, and an 8 higher reward than a 7, and so on. And if the multivariate neural representations of these people are ordered in a way that is consistent with the way these stimuli, after all, are rewarding, then that probably shows that they have a better grasp of the whole situation and that can improve their behavioral performance.
So when you when the participants are making the decision, so this would be like in the behavioral results that you have, do the essentially my question is like if they see a 9 at that, like do they stop sampling very early, because it's very unlikely that they would receive a number on the end of that number line. Like that would be very unlikely if it was a low choice pool. Does that make sense? Or perhaps I misunderstood exactly how you were doing this two choice, like how the distribution of samples from the two choices was going to work out.
Yeah, so they could sample from either option and draw numbers out of the options, and they would get an impression of how often one option or the other option would provide higher numbers or lower numbers. So each of these options had an expected reward, and this expected reward was different. And the task was mainly to find out what's the better option in the long run. And what you're saying is what we see partially in the data, that when participants experience these extreme numbers, for example, a 9 or a 1, which were the bounding numbers, so there were rewards from 1 to 9. If they saw a 9 or a 1, they reacted slightly differently. We see that in ERP amplitudes that, for example, the P3 amplitudes were U-shaped actually, so that the extremes had a much higher amplitude compared to the other numbers. So there's definitely something that we are also still looking into with these extreme values.
Yeah, because that makes a lot of sense, because that's where like the majority of the information is in these cases, and it also it also is the maximal differentiation in the RSA. So is there any way that you can is that something that you feel that you need to control for in the representational similarity analyses, or is that a facet of a facet of the data that's actually helpful for you, is the question. Like,
yeah,
how do you
thanks
think
for that
about
question. That's a great question, and we have considered that, and we also have a second RSA model. So I have shown you the number line RSA model. We have a similar model that we call the extremity model, and in that model, the extremes are more heavily weighted. So that's a model that would weight a 5 as more
Like
similar to a 6, and the extremes to be more similar to each other, so a 1 and a 9. And we did analysis with that model as well on the data, and we did analyses where we orthogonalized the extremity model and the number line model to see whether the number line model still has the effect that we find after we partial out this extremity model. And that is what we find. So the number line effect that I showed in this presentation is preserved. And however, the results with just the extremity model are still a bit inconclusive. So I didn't share them today, but we're still working on that and trying a couple of things, thinking about on how to share these results.
Yeah, that's really encouraging, because that does suggest that it's about the number encoding rather than being about this kind of information content. So in the replay trials, are they replayed previously what they'd already seen, or are they replayed so that way if they did end up seeing one of these extremes, they would notice to make that selection? Or is it like a randomly generated new stream of numbers and it's just matched for the number of samples that they chose?
So these are actual, these are actual replays, and
okay.
But these are replays where the participants are unaware that they are the replays of their own stuff. So a participant would, for example, come in, do the first part of the task where they actively sample, then there's a short break, and then they would see the replay of what they just did. And we always perform post-hoc interviews with the participants to get an idea whether they realized that. And actually none of them did, which is maybe understandable given that they are sampling like 1,200 times.
Yeah.
Now, difficult thing was to counterbalance these things. So when a participant comes in and he's supposed to see the replay first and then do the active sampling, that's obviously impossible logically. So for these people who started with seeing the replay, they actually saw the replay of another person. And that is just how you have to counterbalance it. It's a small compromise that you have to do for this kind of experimental design.
Yeah, I think that makes a lot of sense. And always, I suppose depending on just how greatly people's the influence of how great of individual differences they are, actually crossing people's participants' experiences also seems like it could be a reasonable thing to do. But the counterbalancing is tricky there if you want to actually represent participants their own experiences. Cool. So I think thank you for that. I think we need to wrap up here. I want to thank our speakers again for this session, and the audience for listening. We hope you guys tune in to future Neuromatch sessions as they continue on in the week. And yeah, have a nice day, everyone. Ciao.
Bye-bye.
You too. Thank you.